Hi folks, and welcome to Open Analysis Live. So today we're going to take a look at a piece of ransomware called troldesh, or shade ransomware as I know it, and we're going to look at how to unpack it. And after it's unpacked, I'm going to show you a quick trick to decrypt the strings and rebuild the imports. Really easy, sort of a lazy man's way to rebuilding imports and decrypting strings. And hopefully it's going to save you some time. I know myself, when I'm triaging malware, I usually don't want to get into like how strings are being encrypted or decrypted. I kind of want to just jump over that and get them out there so I can identify what the malware is. So hopefully this trick is helpful for you guys. So with that, let's jump into what this malware is. So if you guys aren't familiar with Any.Run, it's an online sandbox. They're not sponsoring us or anything. I really like what they're doing. They allow you to interact with the samples live. And every week they publish one of these like top 10 malware lists that I pay close attention to. I'm usually really curious to see what the top malware is for the week. And I saw this malware called troldesh, which I'd never heard of before, and I was trying to figure out what the heck is that. So I decided, okay, well, maybe I'll make a video on it. I'll dig into it a little bit, and we can sort of work through it together. So first thing I did was I downloaded a sample from VirusTotal that was marked as troldesh by Any.Run, and I popped over to my favorite online sandbox, Cape, and threw it in here and did a little analysis of it. And if you look at the behavioral analysis here, you can see that there's actually only one process. And if you remember from some of our other videos, when you see malware running and there's only one process, that means that if it's using a packer, that packer has to be doing self-injection. So when it comes time to unpack this, I'm gonna have to keep that in mind. The other thing that I saw here was there wasn't a ton of behavior going on here. There wasn't like a lot of stuff happening. And sometimes because Cape is really focused on doing config extraction, sometimes samples don't run as well in it. And of course, it being a public sandbox, you can't run samples for a super long time. Even though they have the timeout option, I think they enforce a smaller time limit than what you would maybe want for analysis. So I use a Cuckoo instance that run with some friends, and I ran the sample for a long time, and what I saw was it dropped a whole bunch of files with the extension crypted and a number. And so this is telling me that it's probably some ransomware. I also saw, if we do a find in here for README, I saw it dropped a README file as well. So what I did was I downloaded that and I took a look at it in Text Editor here, and we can see it's actually a ransom note. So this is definitely ransomware. And so anytime I'm dealing with ransomware and I want to figure out what kind of ransomware it is, there's this great service called ID-Ransomware that a fellow named Michael Giuseppe runs. And basically what he'll do is he'll tell you what the ransomware is if you upload a ransom note. So we just choose a ransom note here that I downloaded from the sandbox. I'll grab the README here, open it up, upload it, and hopefully he'll be able to tell me what it is. So he's able to identify it based on a URL in the ransom note, and he's calling it troldesh. I actually know of it as shade ransomware. I'm not sure why there's two different names, possibly different vendors naming it different things. But yeah, so now I know that troldesh means shade, so I'm a little bit more familiar with what the ransomware is. Also, I'll put links to these tools in the description of the video below. I'll also put a link to Michael Giuseppe's YouTube channel. If you guys are interested in doing some malware analysis of ransomware, he's been posting some really excellent videos lately, doing some analysis, some dynamic analysis, a little bit of static analysis of ransomware samples. And so I highly recommend it. So if you guys are interested, I'll link that below as well. Okay, so now that we know that shade ransomware is also called troldesh, let's unpack it and take a look at it. And remember, what we saw in Cape Sandbox is it actually only starts one process, so that's going to mean some self-injection. So let's hop over to our VM and get started. Okay, so in our VM today, it's the same setup that we always use in our videos, and of course I'll provide a link down below if you guys want to set up one of these for yourself. We have a tutorial where you guys can go and find a free VM license from Microsoft, install it, and then use an installer that we built that'll install these tools for you guys. The only difference today is that because we know this is ransomware, I've actually just disabled shared folders, and I've disabled network connections just in case. Okay, so let's open up x64 debug here, and we'll drop our malware over into it. So we've covered this a few times in some of our videos, and by now you guys probably know that since this is self-injection, our only real recourse here is to look for memory allocation that's going to have a PE file in it. So of course for self-injection they have to unpack the payload somewhere in memory, allocate some memory for the payload to be written into in their own process, write the payload in and then transfer execution to it, or they could unpack the payload stage by stage into some executable memory and then just directly transfer execution there. So in both those cases, we're going to be looking at virtual alloc and virtual protect. So again, like we've covered in some of the previous tutorials, we want to put a breakpoint on the return from virtual alloc, because the return from virtual alloc is where we're going to have the address of the newly allocated memory. So when you return from that call, the EAX register is going to have the return value in it, and the value is the address of the newly allocated memory. So let's do a Control-G here and go to virtual alloc. And we'll jump to it here. And of course, there's a redirect here from the entry point of virtual alloc to the actual virtual alloc function in kernel base. So we're going to highlight, press enter to follow these jumps, enter again. And then here we see the return here. So I'll just right click and add a breakpoint. So now that we have a breakpoint on the return from virtual alloc, let's put one on virtual protect. So I'll just use the command line here to mix it up. So BP on virtual protect. All right, breakpoint set on that. And now we just run and see if we hit those breakpoints and see what's allocated in those memory sections. So let's run here. We hit the entry point as per usual. x64 debug puts a breakpoint on the entry point always. So we hit that. No big deal. Let's just continue running here. And we hit a breakpoint on the return from virtual alloc. So in the EAX register, it contains the address of the newly allocated memory section. So we can right click and do a follow-on dump. And now in the dump here, we can see the newly allocated section. Of course, it's all null bytes because it's just been allocated. So let's continue executing and see if anything interesting gets written into this section.
You were the clock that was ticking in my home. Change my state of mind.
Ladies and gentlemen,
Love so hard to find.
we got him.
You know, that was pretty simple, right? It's almost like I picked these for the tutorials, but I promise I didn't. This one, we can see that it looks like they've actually written if I make this bigger, they've actually written the header for a PE file into the section here. So you see the MZ and the DOS string here. And if we scroll down a little bit, you can see PE, and there's probably going to be some sections down here. Yeah. Oh, UPX. Interesting. Okay. So there's some section names here called UPX. So let's dump this out, and we'll take a closer look at it before we continue with the debugger. So to dump it out, we're going to right-click, follow in memory map, and then right-click on the memory section and dump memory to file. And we'll dump it to the desktop here. Okay. So now that we've dumped it out, let's open it up in PEBear. Okay, so now that you have it open, we'll look at the section headers here, and indeed the section names are UPX0 and UPX1, and a lot of you are probably familiar with that. Those are the section names for UPX, a universal packer. It's been around since before I started reverse engineering stuff, and it's actually one of the packers that I learned how to reverse engineer with. And I'll show you a trick to actually unpack this in a second. But let's take a look here, and what I'm going to look for is I'm going to look to see whether this dumped out PE file was in its mapped format or unmapped format. And of course, we've covered this in many tutorials before, but just a refresher, if it's in its map format, that means that these sections will be allocated at the virtual address. And if it's in its unmapped format, they'll be allocated at the raw address. And the reason why we need to take a look at that is because when Windows loads a PE file, it expects it to be in its unmapped format, so it expects the raw address offsets for the sections. And of course, if you dump a PE file from its mapped format, you'll need to actually edit the PE header a little bit to unmap it, basically, so you can use it in your tools and you can run it in Windows. And normally the way I would determine this is I would actually look at the raw address offset in a Hex Editor, and I would look to see if it was all zeros or if there's actually code there. So if it was all zeros, it would mean that that section had been moved to the virtual address. But because this is UPX, UPX works a little different from most PE files. As you can see here, the raw address for the two sections start at the same offset in the file. And then when the file is mapped, they actually allocate extra space for the first section. So they add some extra space in there. Now, this means that if you look at the unmapped format of UPX, it could look a lot like the map format. You can kind of get confused. So what I prefer to do is I prefer to look at another section that's not involved in the UPX packing, so like the resources. And we can see here that it'll start at raw just D2E00. So let's go and open this up in a hex editor and make sure that at D2E00 there's actually some data and it's not zeros, and then we'll know that it's in its proper unmapped format, which I think it is just given on where we dumped it out from memory. Normally if it's in its unmapped format, it means that it's ready to be executed. And if we look at where we dumped it in the process, I think that this is just the first unpack before they allocate it to be executed. It seems too early to me because I didn't see any other allocation of memory. It seems too early to me to actually be executing this file. But again, that's just something that that's just a guess on my part. So let's go and confirm that with a hex editor. So we'll open up our hex editor here, pull the file over, and scroll down to the resource section offset, which was D2E00. All right, so here's D2E00. Now you might be a little fooled. You might say like, hey, there's a bunch of zeros there, but you can see there's actually a 1 here. So that is indeed the beginning of that resources section, and it is in its unmapped format. If this was in its map format, I'd expect to see it look kind of like this, where you have rows and rows of null bytes all through the section here. So just a little tip, this looks like it's in its unmapped format. And so now what I'm going to do is I'm going to show you guys how to unpack UPX without a debugger. Okay, so I've popped over to my other VM that I use for static analysis. So I have like ID installed in this and a couple other tools that I use for static analysis. And what I'm going to do is I'm going to show you guys that UPX, as probably most of you know, actually can just be unpacked with the same tool that you use to pack it. So the UPX utility has a -d command, which will actually just unpack any UPX files. So I have it linked to my path here. So if I just open up command line here, and the file that we extracted is sitting on the desktop here. So if I pop over into desktop, and I can run UPX-d shade, and here, it's unpacked the file. So that's pretty much all there is to it. Now we have an unpacked sample, and what I'm going to do now is open it up in IDA and see if we can't figure out what it is, if it's the final stage or if we need to do a bit more work. Okay, so let's take a look at this now that IDA is finished analyzing. So we can see that we do have a well-formed PE file here, and if we look at our imports, looks like there's lots of imports here, which is good. And if we look at our strings here, there's like a ton of strings, but there's something not so great about this. So if you look at these strings, this is kind of something that you'll just sort of learn as you reverse engineer more samples. But a lot of these aren't actually related to the malware itself. I kind of know this just because I'm familiar with these type of strings. So you can see things like Microsoft C++ runtime library. I think there's a bunch of other ones that I saw before when I was looking at this. Yeah, so we can see like some like OpenSSL strings and stuff like that. Usually when you see a lot of these strings, again, this may seem like magic at first, but really it's just you look at enough binaries, you get to learn some of these strings. What these are is actually, these are statically compiled libraries. This is code for libraries that the ransomware developer has decided they want to include in their binary. And instead of referencing those libraries like you normally would, you'd dynamically link them. So at runtime, you would basically like load a DLL and call into that DLL. Because some of these libraries won't exist on all systems, what the developer has done is they've done some static linking. So that means that this file is going to be huge and it's going to contain a ton of like not garbage code, but code that we don't care about, that's not related directly to the ransomware. Code that's only related to like the libraries that they've compiled in. And we can see a few things, like we see like obviously they've added the OpenSSL library. I think they added a crypto library, a bunch of other stuff. So this is a real pain if you're trying to analyze malware quickly, because you can sometimes end up reverse engineering functions that aren't really related to the ransomware. They're related to the libraries. There's a couple projects out there that try and basically create signatures for these libraries so you can identify the functions automatically. None of these projects have really worked out super well. Obviously Flirt, which is the one that IDA uses, it's a set of signatures. That's the reason why we have all the markup here. automatically added. So Flirt comes with IDA. It's probably the best out there, or the best maintained, I guess. There's also one from Talos, which I'll link below. CrowdStrike had one which died, unfortunately. It was pretty decent. But all of these basically require you to sort of submit signatures for known library files or shared code basically to a server, and then when you run your sample, IDA will like pull down these signatures and apply them to try and differentiate known code from unknown code. And again, I don't have any of this set up in my VM. None of it really worked super well as far as I could tell, so I don't really bother. The way that I do it is to basically try and follow the control flow a little bit better, so you can kind of tell if you go a little bit slower and you kind of try to identify where they're calling into libraries versus where they're actually doing some work. That's the best way to do it. But unfortunately, it's still a pain. It's still pretty slow going. So if we look at the main function here, winMain, I actually can see something right away here that I know is a problem. I can see this call here, and it's a call into a memory section, or like basically an offset, so 5FF8D0. And anytime you see something like this, there's basically only two things that could be happening. So anytime you see a call to something that's not a function, something that looks like it might be a pointer, and if we look at it, it's just an empty pointer. So anytime you see something like this, there's really one of two things could be happening. Either one, this is a dumped malware sample, and when you dumped it, you didn't copy the references properly. So we've talked about this in other videos where we talk about having to rebuild an import table or an import address table when you've dumped out a file. So you might see this kind of scenario if you've dumped a file and you didn't dump it correctly, or you need to fix the import address table. That's one scenario. We know that that's actually not the case though, because this was UPX packed, so it means it wasn't running when we dumped it. We had to actually unpack it, and then now we're looking at an IDA. So we know it's definitely not that case. So the only thing it could be is the second case, which is that they have a dynamic import address table that they're building, or they're resolving APIs dynamically at runtime. And so in order to reverse engineer the sample, we need to figure out what these APIs are. These are probably API calls. The best way to do this is actually just to look at the cross-references. So we could press X here, it brings up the cross-references, and then look at what's actually happening to that address. So here we see a bunch of calls into the address, which is what we see here. So that's where it's being used as an API. But we see here is what we're looking for. We see a value actually being moved into that address. So we have a move EAX into that address. So that would be where they're actually setting up the pointer for the API. So what we want to do is we want to take a look at that function there. And here we go. So it's exactly what I would expect to see. They're doing some get procedure addresses to resolve APIs. The return from that is coming back in EAX, so that's a pointer to the procedure address that they resolved, and then they're moving it into a memory section. You can see they're doing it for a whole bunch of different strings here. Now, something else that I see is when you use get procedure address, get proc address, you need to pass it in a string that contains the name of the API that you want to resolve. And I can see here that they're actually not passing in anything that looks like logical strings. This is just a bunch of garbage. So this is telling me that not only are they resolving APIs dynamically, they also have encrypted strings. So we're going to need to do two things in order to statically analyze the sample. We need to find out how they decrypt the strings, decrypt them, and we're going to need to build that import address table so that we have the APIs to look at. And I'm going to show you guys a trick today, something that I use all the time. Basically, when you have a scenario like this, and I'll just pop back so we can see the function here. When you have a scenario like this where you have encrypted strings and they're all being resolved as APIs in one big function, so if we scroll up here, we can see there's a whole bunch of them all in the same function. Sometimes what you might be able to do is actually just use a debugger to run that one function. So if we scroll down here, I don't really see anything else in the function where they're calling out to any other calls that might be not related to this import resolving. So if you see something like this, what you can do is you can actually go and find where the function's called. If it's called relatively early in the execution, you might be able to actually just debug over it and then capture the unencrypted strings and the resolved APIs. So let's just do an X for xrefs, and it's actually called from winMain, so we might get lucky here. Yeah, it's the second function that's called. And we know that they're probably not, well, we don't know, but we suspect that they're probably not going to do any encryption or any ransomware activity until they've actually resolved those APIs and built up the strings. So it's probably safe to actually just debug over this. So I'm going to show you guys a trick using IDA's debugger. I know, but it's good for some things. And this is one of those cases where you'll see it actually makes things really easy. So if you guys aren't familiar with this, IDA actually comes with a built-in debugger. It's actually sitting in the IDA folder. So if you go into Program Files and IDA, and then Debug Serve, there's going to be a Win32 remote debugger. So you can actually just copy it over to your debugger VM. Don't run the debugger locally with IDA. That's definitely not a good idea, especially for ransomware. You're going to go and encrypt your IDA instance, so that's not good. So actually copy this over, the remote debugger, over onto a second VM. We're going to use the VM we were using earlier in this video, and then you can actually just remote debug in that VM safely from your IDA VM. So I'm going to copy this over to the other VM, get it set up, and I'll show you how this works. Okay, so here's our debugging VM, nice and cleaned up here. Here's the IDA debug server, so I just run it, and you can see that it shows you the IP that it's listening on, so that's the IP of the VM, which of course your IDA VM will have to be able to reach that IP, and then the port that it's running on. And I've also copied over the Shade ransomware binary onto the desktop here, so that it's in the same path as the binary that's sitting on my IDA host. So if we hop back over to my IDA host here, what we can do is we choose remote Windows debugger here. Then we go to debugger, we do process options, and we add the host name of that host, 136. So 67.136, 67.136. And like I said, the malware is going to be sitting on the desktop. Now on the input file, of course, the user for our VM here is not analyzer. Our user here is admin, I believe. Yeah, it's admin. So we're gonna have to change that path over in IDA. So in here, we're gonna go into here and change that to admin. Okay, and then what we want to do is we want to add a breakpoint on the entry point here so that we don't run past it. So add a breakpoint, and then we'll try and run it. So actually I changed the wrong path for the remote process. So what I'm going to do is I'm just going to say, like, just use the binary that we've loaded in IDA as the one that you're going to run in the debugger. So I'll say use found. Okay, so we've run now, and we've hit our breakpoint on the entry point to win main. And what I'm going to do, this is actually IDA's debugger view. For those of you who haven't seen this before, to clean it up, we can go into like view, toolbars, advanced mode, switch to advanced. We get our buttons back here. Of course, I don't really care too much about the console window. I want to see a little bit more of the stack here, and our registers are up here. So I'm going to sort of minimize the threads a little bit in the modules so we can see our registers a little bit better. Okay, but we're not really going to be doing too much debugging here anyway. We know that it's actually the second function here that's doing the decryption. So if you look here in the drop down, you can see that's actually doing the resolving of the APIs, and the strings must be decrypted in order for that to happen. I think that this might actually be the decryption algorithm. Again, we don't really care because we know that when they're resolving the APIs, the strings will be decrypted. So as long as we jump over that function, everything should be good. So we're just going to press the jump over command here, jump past the first function and past the second function. So we can see now that in this pointer here, we actually have a pointer to an API. If we sort of hover over it, we can see that it's kernel32 get current thread ID. So it's actually been resolved. And now here's the thing. You could have just done this in a debugger and like copied over those strings. You could use a script maybe. I know there's some scripts for Ollie to actually copy over those references and put them in the right place in IDA. But here's the trick for IDA. All you have to do is go into the debugger and do a take memory snapshot. And yeah, we'll do all segments here. Now this grabs a ton of extra data, and it's going to make your IDA IDB kind of slow. But it doesn't really matter too much because once it's loaded up, it's fast enough. And if you have enough RAM and enough disk space, it doesn't really matter too much. So once you capture this, you can actually terminate the debugger. So now that we've captured it, you can kill the debugger here, and it's going to take a minute to sort of reset itself. And all of those references, the decrypted strings, the rebuilt import table, all of that's actually going to be populated in your static IDB now. So then you can just continue static analysis without needing a debugger. It's like a pretty cool trick. I use it all the time when I'm lazy and I just want to decrypt strings quickly to try and figure out what a sample is doing. And I'll show you what that looks like here. Okay, so now we've gone back to our static view. The debugger is not running anymore, and check this out. So if we go into our offset here, we can jump into it, and we can see that it's actually been labeled here. The label is still applied to that offset. So if we pop in here, we can see here that it's actually copied the kernel 32 DLL into our IDB with the appropriate offsets labeled for each API. And so then we can see that this reference to the kernel 32 address is actually now being labeled in IDA. This makes analysis way, way easier, and I'll show you what I mean here. So if we pop back here and we go into this function where we were using the encrypted strings, which should be decrypted now, to build the import address table, if we look at these strings now, you can see that they've actually been decrypted. So it's no longer this gook stuff. Now you might be wondering, well, why is it showing me the decrypted string, but the variable name is still the sort of encrypted blob string? And this is because IDA just doesn't know that that string value has changed. It needs to reanalyze it. So we can do that, and that should repopulate those variable names. We also can see now that each one of these references here, so this would be, let's say, this is get logical drive string W is being resolved by get proc address. EX was being moved into this pointer here, and if we go to that pointer, you can see that there's a reference now. It's not null anymore, and that reference, if you hover over it, is to kernel 32 get logical drive string W. So you can see that it's all been populated now. Now, of course, this still looks kind of janky because IDA hasn't reanalyzed. It doesn't know that the pointers are to these different offsets. So we can actually try and do a reanalyze here. So we can go into options, general analysis, and we can force it to reanalyze. And now this is going to take forever. So we're probably going to have to time lapse this. Okay, so now that that has completed analyzing, we can see we have a much different picture here. All of the strings have actually been renamed. The variables for the strings have been renamed. And we now have references, labels for all of these APIs that have been resolved. So that's pretty much a quick trick that you guys can use if you don't want to figure out what the decryption methods are manually. Just use this trick, load up the remote debugger, and run past the function that has the decryption in it and the import building, take a memory snapshot, and then just simply have IDA reanalyze the binary, and it should apply all the labels for you. So there we go, unpacking in 2 steps and string decryption in 2 steps as well. So hopefully you guys can use these tricks going forward. So with that, we pretty much wrap this up. Pretty quick tutorial. And again, hopefully you can find some of these techniques useful for your own analysis. And until we meet again, keep exposing the mechanics behind the malware. Stay curious.